AQA Physics GCSE Paper 1 revision video. So in this video, everyone, I'm going to be walking you through all the content and the required practicals that you need to be aware of for Paper 1 Physics GCSE. Those of you who've taken separate sciences, yeah, it used to be called triple science, but that's what it's called now, separate sciences. If you don't know who I am, my name is Mr. Ceerazzledazzle. I'm a qualified physics teacher with over 15 years of teaching experience. I've also worked for the BBC and ITV, but now I simply make content online on my YouTube channel, Ceerazzledazzle Physics. The way you should use this video is that you should obviously go to class and obviously learn from your teacher there, but this is a nice revision video to refer to before the exam. There are some kids who actually use it, they play it in the background, and obviously they listen to it as an audio book. That's also quite helpful because obviously the more you view it or the more you listen to it, the more it will sink in. So get ready guys, this is going to be everything you need to know. It's a long video, but I hope you enjoy it. Let's start in 3, 2, 1, go. Okay, so energy and energy stores. Energy can never be created or destroyed. It can only be transformed from one form to another. Energy is measured in joules, capital J. In a closed system, the total amount of energy remains constant. So that means that in a closed system, let's say all the energy coming in is equal to all the energy coming out. It's not going to change. Right, there are different types of energy stores. Over here on the left hand side you'll see a table which has everything in it. We've got the energy stores, description and some examples of it. So there are 1, 2, 3, 4, 5, 6, 7, 8 different types of energy stores. Magnetic, internal, chemical, kinetic, electrostatic, elastic potential, gravitational potential and nuclear. Description, so I'll walk you through an example of each one. Let's say you have two magnets, you put them together, opposite poles. Obviously that's going to be magnetic energy stored. Internal, let's say you have a kettle, you turn it on, the particles gain kinetic energy and they're moving around a lot. That will be internal energy. Chemical will be the energy stored within chemical bonds. Kinetic is going to be the energy of any moving object. Electrostatic, let's say you have two protons, they're positively charged, you bring them close together, they want to repel each other away, that's going to be electrostatic energy. Elastic potential, when you compress, let's say, a spring, it will have elastic potential energy stored. Gravitational, if you have an object, you put it into the air, it has the gravitational potential energy of falling down. Nuclear is going to be the energy stored within the nucleus of an atom. So that's going to be nuclear energy over here. Right, now, energy pathways. So right now, look, over here on the right hand side, I've got an example of a ball falling down. We know that energy can be transferred from one form to another. So over here we have gravitational and we know it's going to be converted into kinetic as it falls. Yes, gravitational at the top, drop it, it becomes kinetic. Obviously to go from here to here, there is a mechanism. This is going to be the pathway. So this one is going to be called mechanical working helps this to occur. Okay, so there are 1, 2, 3, 4 different energy pathways. And look, here's a description of each one of them. Electrical working is going to be when you have a flow of charge in a circuit. Heating via radiation, that's going to be when you have electromagnetic radiation such as light or radio waves or gamma waves which are traveling, they're transferring energy via electromagnetic radiation. Heating via particles is going to be when you have objects which are gaining energy, let's say or you have a warm object next to a cold one, obviously it's going to be a transfer of energy in that process. And mechanical working is going to be energy transfers via forces such as pulling, pushing or stretching. So look at this one over here, we know it's going to be, this is a force obviously making it to fall down, that's why it's mechanical working over here. The next one, here's our first formula for kinetic energy. All objects have kinetic energy, so kinetic energy is equal to a half times by the mass times by the velocity squared. Okay, and here's our formula, E is equal to a half times by m times by v squared, where m is the mass in kilograms, the velocity is in meters per second, and the energy is in joules. Right, the next thing we're going to talk about is what happens if you were to double the mass or double the velocity, and the effect it has on the kinetic energy of an object. Well, look over here, I've got two different tables. The first one, you can see that I've doubled the mass but kept the velocity constant. Obviously, what happens is the kinetic energy doubles as well. If you plug it in, plug these values in, you'll be able to see that for yourself. And look over here, I've done the reverse. Well, I've kept the mass constant, but I've doubled the velocity. You can see that because the velocity is squared, that we get 4 times the amount of kinetic energy over here. So doubling the mass results in double the kinetic energy, but if you double the velocity, you end up with 4 times the kinetic energy. So just make sure that you're happy with that, be a little bit of extra information. Elastic potential energy. So let's say we have a spring and we were to put a weight at the end of it, it will extend to a final length F. To work out the extension, I'm going to do F minus L, that will be the extension of the spring, how much is actually gained length over here. To work out the elastic potential energy, I can use the following formula. Half times by the spring constant times by the extension squared. So E is equal to a half times by K times by E squared. K is going to be the spring constant. That's basically a measure of how stiff the spring is. Okay, if you look at the units then, energy is in joules, spring constant is Newton per meter, and we've got the extension in meters over here. And on the right hand side, I've done a little quick walkthrough. Let's say we have a spring of a spring constant 10 newtons per meter and extends by 5 centimeters. Just plugging it in, half times by 10 times by, careful with this one, convert centimeters into meters, 0.05 squared. We'll get this value over here. So make sure you're happy with that. Next one, gravitational potential energy. Gravitational potential energy is going to be energy is equal to mass times by gravitational field strength times by the height. E is equal to mg delta h. Energy is measured in joules, mass is in kilograms, gravity is going to be newtons per kilogram. That will be dependent upon which planet that you're on. Gravity on Earth is always 10. So gravity on Earth is always 10. The height is going to be in meters. And look, in this example, let's say we take a block of 5 kg, we raise it 10 meters into the air. The energy is equal to 5, the mass, times by gravity. On Earth, it's going to be 10 times by 10 over here. Yes, because obviously the height was 10, it's going to be 500 joules. Alright, so next thing, specific heat capacity. Right, this is a difficult concept. The specific heat capacity of an object is the energy required to change the temperature of 1 kilogram of a substance by 1 degree Celsius. Okay, alright, so it sounds quite complicated, but the basic idea is going to be this. Different objects require different amounts of energy to heat them up. Yes? So very good example at the bottom, I've got the specific heat capacity of water, and I've got the specific heat capacity of oil. We can see that specific heat capacity of the water is 4,200 joules per kilogram degree Celsius, and the specific heat capacity of the oil is 2,000 joules per kilogram degree Celsius. So what does that actually mean? That means that it's going to be much easier to heat up the oil than it is for the water, because you've got to put this much energy in, you know, to heat up the water compared to this much for the oil over here. And look, my summary statement, the greater the specific heat capacity of a material, the more energy is required to change its temperature. And here's my formula we can use. The energy is equal to the mass times by the specific heat capacity times by the temperature change. E is equal to mc delta theta. Energy is in joules, mass is in kilograms, specific heat capacity is joules per kilogram degree Celsius, and the change in temperature is degrees Celsius. This little triangle stands for the change in temperature over here. And look on the right hand side, I've got an example. A bowl of water of mass 100 grams is heated from 5 degrees Celsius to 45 degrees Celsius. Given that specific heat capacity of the water is 4,200 joules per kilogram degree Celsius, calculate the energy transferred. So look, E is equal to mc delta theta. Yes, the mass, convert this into kilograms, 0.1. Specific heat capacity is 4,200 times by the temperature change, which is 45 minus 5, which will be 40. And that will be our answer over here. Okay, so the required practical, how to work out the specific heat capacity of an aluminium block. Here is an aluminium block over here, there we go, and you need the following bits of apparatus. You need a heater to put it into the block, thermometer, and then you need a circuit. A voltmeter is connected around the heater, and an ammeter is connected in series with the heater over here. Right, so the equipment, look, voltmeter, ammeter, power supply, stopwatch, aluminium block, thermometer. These are all the things that you need over here. Method, so you set up the diagram, so to set up the apparatus as shown in the diagram, turn on the power supply, and obviously the heater will start to heat up the aluminium block. Every 60 seconds, you record the voltage, or the potential difference, and the current from here. There we go. So we're going to get the voltage and the current over there. Right, in order to work out the energy, you can use the formula. Energy is equal to I times by T times by V. ITV will give you the energy over here. So that's how we do it. Risk assessment, obviously the block starts to heat up. Do not touch the block when you're heating it up. Use heat-proof gloves when handling the block. Maybe you place the block on a heat-proof mat. The control variables, keep the aluminium block the same. Do not change the power supply voltage as well. So you obviously do not change the block throughout the whole thing or the power supply voltage. Right, now regards to results, what we're going to do. Right, you can plot the following graph then. If you plot temperature on the y-axis and energy on the x-axis, you can see that we've got this line over here going up. We've got this nice line going up over here. Right, so once you've plotted this graph, this is quite difficult. So first of all, look at our formula. We can see that energy is equal to mass times by specific heat capacity times by the temperature change. Your task is to work out the specific heat capacity. Well, look over here. If you rearrange this formula, it becomes E divided by m delta theta. And then the gradient of this line, what are you doing? It's the change in temperature divided by the change in energy. So that's why you can put that at the bottom over here. So that's why, look, this delta theta over delta E can go into this one over here. So look, we have 1 divided by the mass, and that represents the gradient of the line. There we are. So therefore, if you have a 1 kilogram mass of the actual aluminium block, therefore the specific heat capacity is 1 divided by 1 times your gradient, because obviously the mass is 1 over here. So when you do this experiment in class, you work out the gradient of this line, and the specific capacity will be 1 divided by 1 times by the gradient, which you found out from your practical. Right, power. So power is the rate at which energy is transferred. Power is measured in watts. Okay, so power is measured in watts. So look, we have the following formula. Power is equal to energy transferred divided by time taken. P is equal to E divided by T. Power is measured in watts. Energy is in joules. Time is in seconds over here. There we go. And look, here's an example. If a hairdryer transfers 1,000 joules in 20 seconds, the power of the hairdryer is going to be 1,000 divided by 20. It's going to be 50 watts. Energy transferred is equal to the work done. So also, you might find that you get a small variation in terms of this formula. Power is also equal to work done over time. So power is equal to W divided by T. But still, it has the same units. It's going to be watts is equal to joule divided by seconds over here. Energy efficiency. So to work out the efficiency of an object, you simply have to use the following formula. It's going to be the useful energy out divided by total energy in multiplied by 100. Or the useful power out divided by total power in times by 100 over here. And look, we've got this example. Let's say we have a light bulb of 100 joules going in, 80 joules of light coming out, and the heat is 20 joules going downwards. To work out the efficiency, it's useful, 80 divided by 100 times by 100, 80%. You can leave it as a decimal, so you can take it as 80% or 0.8. Both are fine over here. There we go. Right, next one's going to be energy transfers in a system. Obviously, a system is an object or a group of objects. In a closed system, there is no net change in the total energy. Okay, thermal conductivity. So imagine you have a wall with a window in it. First of all, the window will let out more heat through it compared to the wall. Hopefully that makes sense. Look, there's got greater arrows coming out of the window, and look, the wall has less of it, less of those arrows coming out. We can say that the window has a higher thermal conductivity. Yes, so the greater the thermal conductivity of an object, the more the heat can flow through it. And look over here, the thermal conductivity of an object therefore affects the rate of cooling. And look, I've got different materials, brick, steel and glass. We know that the glass has the highest thermal conductivity because the heat can flow through easily. Brick has the lowest. That's the reason why you build bricks around a house, to keep the heat in, obviously. Required Practical 2, Part 1. Investigate the effectiveness of different materials as thermal insulators. So in this practical, we're going to change the type of insulation around a beaker and see which one's going to lose heat at the fastest rate. Right, so it's a really easy practical. The equipment you need is going to be 5 beakers, 5 lids, 5 thermometers, kettle, different insulating materials to wrap around the beakers, rubber bands and stopwatches. Right, so number one, what you're going to do is you're going to get the beakers, put different types of insulations on each one of them. Yes, let's say newspaper, cardboard, bubble wrap, etc. Pour equal amounts of hot water into each beaker. They should also be the same starting temperature. And then you let the temperature rise to the highest value, obviously because when you put the thermometers in, the temperature will go up. And then you start a stopwatch, and then as time goes on, you record the temperature on each of the thermometers. And obviously all the water will cool inside them. But then you'll look at each different type of insulation. You will notice that the temperature change will be different. Risk assessment for this, you must use gloves when handling the hot water or beaker, as the heat can scald the skin. Control variables, you can use cans of the same surface area, so you have to use them obviously. Put equal amounts of water into each beaker. Obviously put more hot water into one, it wouldn't make a fair test. Keep the temperature of the surroundings the same. If you change the temperature of the surroundings, it will change the rate of cooling. Also, you must keep the same thickness of each insulator. So obviously you can't have one insulation like twice the thickness as another. Okay, so let's say we look at the results, guys. So let's say we plot the graph of temperature versus time for each one of our different types of insulation. Hopefully you can identify that the best insulator will have the least change in temperature. So look over here, it goes from there to there, it has the least change in the temperature. And obviously the worst insulator will have the greatest drop in temperature over here. So make sure that you're happy with that with regards to your results. Next one, Required Practical 2, Part 2. Investigate the factors that may affect the thermal insulation properties of a material. So I've got 1, 2, 3, 4, 5 different beakers right now, but we're going to keep the type of insulation the same, but we're going to change the thickness of it. Okay, so in the previous practical, we changed the type, we kept the thickness the same, but now we're going to keep the type constant and we're going to change the thickness. So in this one, 5 beakers, 5 lids, 5 thermometers, kettle, newspaper, stopwatch, rubber bands. Obviously, same thing again, you put equal amounts of water, you wrap different amounts of the same material on each one. So look, this one's maybe 1 layer thick, 2 layers, 3 layers, 4 layers thick, but it's the same material right now. And then you put the equal amounts of hot water into each one of them. And yes, you let the temperature rise up to the highest value. Once again, start the stopwatch, and then every minute record the temperature. So you're recording the temperature each time as time goes on. Obviously the temperature will drop for all of them, but some of them will drop faster than the others. The risk assessment, obviously use gloves when handling the hot water or beaker as the heat can scald the skin. The control variables, use cans of the same surface area and volume. Put equal amounts of water into each beaker. Keep the temperature of the surroundings the same throughout the investigation so it can affect the rate of cooling. So make sure that you keep the temperature of the surroundings the same. And look at my table of results. We've got time, insulation. We've got no insulation, 1 layer, 2 layer, and 3 layer over here. So we've got 1 layer, 2 layer, and 3 layer. Hopefully you can identify that. The results will look like the following. So the beaker with the most layers of newspaper will have the smallest change in temperature. Why? It's the best insulator. Obviously because it's got the greatest amount of layers on it. And the beaker with the least amount of layers of newspaper will have the greatest drop over here. Just like a jacket, yeah. Obviously, like you're wearing multiple layers, you're obviously going to lose heat at a slower rate compared to someone with a very thin jacket. It's the same idea. Now, we're going to move on to energy resources. There are 2 different types of energy resources, non-renewable and renewable. Non-renewable simply means energy resource, once it's used, it cannot be used again. Renewable resources will not run out and therefore can be used again and again. Some examples of the non-renewable are going to be coal, oil, and natural gas, and nuclear. Renewable will be solar, wind, geothermal, hydroelectric, tidal, biomass, and wave. Right, so the fossil fuel power stations, coal, oil, and natural gas. So look, fossil fuels are burnt, heats up the water turns into steam. Steam then flows through the turbine, which connected to the generator, which generates electricity. So make sure you're happy with that. And then the advantages of the fossil fuels is going to be, number 1, it's a reliable method of energy production. Fuels can be easily transported. Disadvantages, it's non-renewable. There's a finite amount of the fossil fuels. Coal, oil, and natural gas all release greenhouse gases which contribute to global warming. Coal releases nitrogen oxides and sulfur dioxides which can contribute to acid rain. The greenhouse effect in global warming. So right now, this is going to be a disadvantage of using the fossil fuels. The sun's rays, infrared rays, should be able to travel down, hit the Earth's surface and be reflected off it. But look over here. If you were to burn fossil fuels like cars, they obviously are burning the oil, it produces greenhouse gases. Those greenhouse gases emitted will then form a layer around the Earth. And now this is called a greenhouse gas layer. Now the radiation from the sun, when it hits the Earth and it reflects back upwards into space, it can no longer leave, it reflects back inwards. So the heat is now trapped. And obviously the heat is trapped, that causes the temperature of the Earth to increase, and this is going to be the origin of the global warming over here. Right, so now from here we're going to move on to the different types of renewable energy. So first of all, wind power, giant turbines, hopefully you've seen them, they convert kinetic energy into electrical. The advantages are, number 1, it's renewable. Once you've set it up, it doesn't cost that much to keep running. There's no greenhouse gases emitted, and it can be installed offshore. Disadvantages, it's unreliable, it may not always be windy. There's a limited locations available, yes, so maybe people don't want them in their back garden. There's a large number of them required to produce a sufficient amount of energy. They can also kill birds. It can also spoil the visual landscape. So obviously people don't want them putting up in the countryside because it looks a bit ugly. Some of the people might think of that. Right, solar energy. Using solar cells to absorb the light energy of the sun and convert energy into electrical energy. So obviously here's our solar cells. Advantages, renewable. Once set up, has a low maintenance cost. There's no greenhouse gases emitted. Disadvantages, it is unreliable. Limited locations available, areas of high amounts of sunlight are required. There's a large number required for a sufficient amount of energy production. And also you need a large amount of surface area available for you to be able to capture the light as well. Hydroelectric power. So first of all, this is really interesting. Let's say you have at the top of a mountain, there's like a reservoir, the water can collect there. Obviously it rains, it collects over there. And then what happens is they build a dam, and here's the dam over here, and it stops the water, well, it lets the water flow through it, and inside the dam there's a turbine. So as the water drops down, it pushes through the turbine, generating electricity. And here's a good example of a dam over here. So look, it goes from the gravitational potential energy of the falling water, transfers into kinetic energy as it falls downwards. Advantages of this is going to be it's renewable. Once you've set it up, there's low maintenance cost and there's no greenhouse gas emission. Disadvantages though, the dam could break, yes, and obviously the risk of flooding. Construction of the dams can destroy natural habitat, so when you're initially building the dam, you probably destroy loads of animal habitats. It's high startup cost, so obviously making that in the first place. There's a limited number of locations, so only mountainous regions are suitable. The dams can block migration and the patterns of fish, so fish can't swim upstream, obviously because of the dams in the way. Biomass energy. So the byproducts from forestry, plants and animal waste can be burned to produce heat. So that heat is then used to heat up water and then the turbines and the generator. The advantages are going to be, so crops are grown as fuels, so therefore it's going to be renewable. The fuel is cheap and readily available because you're planting each time. And although the plants release greenhouse gases, obviously when you burn it, they also take in carbon dioxide when they're growing because obviously photosynthesis is taking place. Disadvantages, it releases carbon dioxide into the environment. Growing large amounts of certain crops will limit the biodiversity. So that means that if you grow a certain type of one crop, yes, obviously it's going to reduce the variation in crops that you will have in an area. There's also a moral obligation because people might also say that we could be using those crops to feed people and they shouldn't be used to produce energy. Nuclear energy is going to be the following. It's the energy coming from the fission, which means the splitting of a nuclear atom producing heat in that process. Advantages are going to be the following. 1 kilogram of nuclear fuel releases 1,000,000 times more energy than 1 kilogram of coal. No greenhouse gas emission in this whole process. Disadvantages are going to be a risk of a nuclear disaster, therefore the risk of radioactive material being released into the environment. Decommissioning is going to be when you're trying to dismantle the nuclear power station once it's finished. It's very expensive and quite dangerous. It's also difficult to dispose of the nuclear waste. And obviously it is also non-renewable. So make sure you're happy with that. The nuclear energy is non-renewable. Once you've used up all the uranium fuel, which is used for nuclear energy, there will not be any more available for us. Geothermal energy. So this is really interesting. They pump cold water down into the ground and the hot rocks heat up the water, turning it to steam, so it comes back up to the surface as steam over here. As you can see, the advantages are it's renewable. It's, once you've set it up, low maintenance cost. There's no greenhouse gas emission. Disadvantages is going to be it's a limited locations available, can trigger earthquakes. Drilling underground can sometimes release greenhouse gases as well. So when you drill underground, it can also release greenhouse gases. Wave energy. So these sit on the surface of the water and inside there, the waves come in and they push air through a little turbine which is placed inside there. And that generates electricity. Advantages, it's renewable, no greenhouse gas emission. Once you've set it up, there's low cost. Disadvantages, only certain locations only. High initial building costs when you're trying to get it going. Turbines can also then stop the, let's say, boats from travelling, and it's unreliable as you're dependent upon the motion of the waves. Tidal energy is slightly different. So this one, you have the turbine placed in the water right now. So this is the turbine placed on the seafloor. Advantages, it's going to be it's reliable and predictable as tides are fairly constant. It's renewable. The tidal turbines move relatively slowly, therefore minimal disruption to wildlife. Disadvantages, there's not a large amount of energy produced, a high initial cost to install the turbines, and obviously because you're sticking them in the water, certain locations only. They can disrupt the migration patterns of marine life as well. Okay, so static electricity. First of all, let's take a jumper and a balloon. Initially, hopefully you can identify that they are both insulators. Yes, so no charge can actually flow through them. And they are initially neutrally charged. That means that they have equal amounts of positive and negative charge. So look, the jumper is positive over here and negative, equal amounts. They cancel each other out. And the balloon as well, 3 positive, 3 negative. They are both neutrally charged because they also cancel out over here. But if you were to rub them both together, what happens is charge can be transferred from one form to another. So look, you can see that the balloon has gained these negative charges over here, which are the electrons. And the jumper over here has lost the electrons to the balloon. So the object which loses the electrons becomes positively charged, and the object which gains electrons becomes negatively charged over here. Right, so now look, this one is positive and then this one is negative. So they've now become charged. And this is the origin of static electricity because now they've both become charged. The charge is not free to flow and therefore it's stuck on the balloon and it's stuck on the jumper over here. Right, so now from here we're going to do the following. We can now hopefully explain why a balloon, if you take it and you rub it against like a jumper, why it can stick to a wall. So over here, let's say the balloon, we charge it, and obviously it's negative charge, and then you were to place it next to a wall over here. Hopefully we can see that, look, what happens is within the wall, the negative charges get repelled away. Obviously, because these ones are negative, they repel these ones away, and therefore the positive charge attracts the negative ones on the balloon, and that's the reason why the balloon sticks to the wall. Hopefully you've seen it as a party trick yourself, and obviously try it yourself. Like, take a balloon, blow it up, rub it against your hair or your jumper, and you'll be able to stick it against the wall based upon this principle. Now, a use of static electricity can be the following. Let's say you were to paint a car efficiently. So what you can do is this: you can charge the car positive, yes, so you attach it to a terminal and it becomes positively charged, and you charge the paint negative. Then you spray the paint, obviously positive and negative, they will attract, and therefore they will stick evenly across the car. So this is a great way to use static electricity to paint a car. Electric shocks. So let's say over here we have a cloud and it's full of electrons over here. The cloud is full of electrons and you're flying a kite. First of all, hopefully you can identify that the electrons over here will want to discharge itself. And that's the reason why we get an electric shock. So this spark occurs from there going all the way down. The reason why is because there's a large potential difference from the cloud and yourself, and that's what causes the spark. And in this case, it's the lightning strike. That's why you see the lightning over here, because it's trying to discharge itself because all the charge builds up. And that's the reason why we get an electric shock, it's because there's a large potential difference, hence why the charge jumps from one place to another. An electric field is going to be the following. It is a region in space in which a charged particle experiences a force. So look over here, we've got two electric fields. This one's a positive one, and look, the arrows are going outwards. Negative one, the arrows are going inwards over here. The direction of the field tells you that if we were to put a positive charge here, it will move along that line. If I were to put a positive charge here, it moves along this line. So the direction of the field lines tells you the direction in which a positively charged particle will move in. This one is a uniform field. The reason why is because the lines are evenly spaced out here. Like school uniform, it's evenly spaced. Everyone's the same idea. 1, 2, 3, all the lines are evenly spaced. This one is a uniform field. The previous one over here, this one is a radial field. The reason why, we can hopefully see that the closer you are to the center, to the actual object itself, the stronger the field will be. The reason why is because the density of the field lines indicates the strength of the field. So over here, because there's loads of field lines in a small bit of area, that's why the field is stronger. But the further away you are, the less strong the field will be. Okay, so now electrical circuits. So we've got to be able to identify the electrical components and the different symbols. So look, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 different electrical symbols. Open switch, closed switch, lamp, diode, LED, cell, power supply, fixed resistor, variable resistor, fuse, thermistor, LDR, ammeter and voltmeter over here. So all of these ones over here. Make sure that you are able to draw them and identify them in a circuit. Okay, so electrical current. So current is simply the rate of flow of charge. Current flows from the positive terminal, the long stick, to the small one going all the way around over here. If you want to measure the current of a component going through it, right now, look, you place the ammeter in series with it. The ammeter is placed in series. So the formula for the current is equal to the charge divided by time. I is equal to Q divided by T. I is measured in amps, the charge is in coulombs, the time is in seconds over here. There we go. Right, so this is called conventional current because the current is moving from the positive terminal all the way around to the negative one. Right, so you might be asked about the electron flow in this diagram. So electrons don't move from the positive terminal to negative. If you were to look at this diagram, you can see that the electrons are going from the negative terminal to the positive one. The reason why? Because the electrons are repelled from the negative terminal. Obviously, the same charges repel and attracted to the positive one over here. So conventional current goes from long stick, positive to negative, but the electron flow is actually in the opposite direction. Right, voltage and potential difference between 2 points. So the voltage is simply the energy per unit charge. Voltage is equal to energy divided by the charge. V is equal to E over Q. That's going to be our formula. The units, voltage measured in volts, energy is in joules, charge in coulombs. If you want to measure the voltage of a component, you place it in parallel around the component over here. So look, it's placed in parallel around the component. There we go. Right, now current in series and parallel circuits. So the rule for current is going to be this. Current in a circuit, it splits at the junction. So that means that the total current going into a junction is equal to the total current out of the junction. So look, there we go, the current comes in, it splits and goes there and there. So therefore, then look at this point over here, these two combine together to make this one over here. So look, you can say that the total current going in is equal to the total current coming out at the junction. So look, this one, IT is equal to I1 plus I2, which is this one over there, and I1 plus I2, as they both recombine, they will make IT over here. Easy stuff. Voltage in series and parallel circuits. The total voltage into a loop is equal to the total voltage out of the loop. So look over here, the sum of the voltage in is equal to the sum of the voltage out in one complete loop. That basically means this. Look, we've got one loop there and one loop over here, back to the center. So look, V in is equal to V1 plus V2. Yes, over there. And also we know that the V in is also equal to V free. So this voltage across here is the same voltage across this one over here. Required practical, voltage and current characteristics of a fixed resistor. So in order to look at the voltage and current characteristics of a fixed resistor, you need the following circuit. You need a power supply, fixed resistor, variable resistor, the ammeter placed in series, and the voltmeter placed in parallel. Right, the method, so obviously set up as shown, then obviously turn on the power supply, and then record the values of the voltage and the current, yes, from the voltmeter and the ammeter. And then you change the variable resistance over here, which will affect the current in the circuit, and then you repeat again, recording the voltage and the current again. There we go. Control variables, keep the fixed resistor the same throughout the entire investigation. Yes, keep the power supply voltage the same each time. You're only changing the variable resistor over here, and recording the voltage and the current of the fixed resistor. Then if you were to plot the graph, you'll recognize that you get a straight line relationship between the voltage and the current over here. Risk assessment, obviously, turn off the power supply in between readings to stop the fixed resistor from overheating as well. Right, now once you've done that, you can then look at the voltage and current characteristics of a filament lamp. So look, it's the exact same circuit. I've just swapped the fixed resistor for the filament lamp. You do the same thing again. Simply just going to change the variable resistance over here and record voltage and current. You end up with the following graph now. So look, it curves off over here. Right, so making sure that you can explain this graph. The reason why you get this S shape is because the lamp starts to heat up the more and more current you pass through it. As the lamp starts to heat up, what happens is the resistance increases. If there's a resistance increase, what happens is the current obviously has to stop increasing. Not decrease, but stop increasing over here. So the reason why the current starts to level off is because the resistance is increasing. Make sure you can recognize that the filament lamp results in this S shape over here. Right, so once you've done that for the filament bulb, you can then do it for the diode. So look, it's the exact same circuit, and what you're going to do is you're going to change the variable resistance and record the voltage and the current over here. And you'll get the following graph, guys, so there'll be no current in one direction, and look, after a while, then the current then starts to increase. So make sure you're happy with this graph as well. So looking at them all together, we can see for the fixed resistor, we get the straight line directly proportional relationship. For the filament bulb, we can see that it curves off over here. For the diode, we can see that it doesn't work in a one direction, then it starts to go up. Make sure you can understand that for the fixed resistor, voltage is proportional to the current, yes, and therefore you can actually say that V is directly proportional to I, and this leads us to Ohm's law, which is going to be the voltage is equal to the current times by the resistance over here. V is equal to I times by R over here. And look, we talked about the filament bulb. The reason why it levels off is because the resistance increases. I'll put that on the board. And the diode is quite important because it only works if it's a certain way around in your circuit. If you put it the wrong way around in your circuit, the current will not flow through it. So if you over here, you can see that there's no current because it has an extremely high resistance in this direction. That's the reason why. So it has extremely high resistance in this direction. And over here, there's a threshold voltage before the current can flow. Right, so now combining resistors. If you want to combine two resistors together, let's say you had R1 and R2 over here, you want to draw another circuit, combine them together, you simply add them together. So R1 plus R2 is equal to RT over here. And here's an example, 10 and 20 ohm resistor, add together, it's going to be 30 ohms in total. Right, if you want to combine them in parallel, so look, these two are now connected in parallel. If you want to make them into one simple circuit over here, you can do 1 over R1 plus 1 over R2 is 1 over the resistance in total. You're not required to know that formula, but just be familiar with it. Right, so let's look at this example. Let's say I have a 10 ohm resistor and a 20 ohm resistor connected in parallel. Look, in terms of the maths, 1 over 10 plus 1 over 20 is equal to 3 over 20 over here. Yes, cross multiply. Therefore, 20 over 3. The equivalence resistance, these two combined together make 6.67. Yes, there's less resistance combining them together. Right, and therefore, to summarize, hopefully you can identify that combining resistors in series, look, it will obviously give you more resistance than if you were to combine them in parallel. Yeah, comparing the left-hand side to the right-hand side over here. Right, then, required practical, factors affecting the resistance of electrical circuits, combinations of resistors in series and parallel. Right, so you say take a cell, you have resistor R1 and R2 connected to an ammeter and return back again. You then place the voltmeter around both the resistors. Then you were to record the voltage value and the current value, and to work out the resistance, the total, you simply do the voltage divided by the current over here. Then you do the same thing for a parallel circuit, so you take the cell, then you have R1 and R2, you have the ammeter returning back again. You put the voltmeter around the parallel combination bit. And notice that you record the voltage again and the current again. And then you work out the resistance by doing V divided by I. And notice, look, the resistance will be 25. So look, obviously there's less resistance when they're in parallel compared to when they're in series. So once again, summary, combining two resistors in a parallel combination will have an effective resistance lower than the two resistors connected in series. Required practical 3. Factors that affect the resistance of electrical circuits. The length of wire at a constant temperature. So you're going to change the length of the wire and you're going to see what happens to the resistance of the wire. So you need a power supply, an ammeter, a voltmeter, the wire itself, crocodile clips, and the wire should be attached to a meter ruler. Yeah, so a meter ruler over there. So you set up the circuit as shown in a diagram. Change the length of the wire. So you move the crocodile clips, you change the length of the wire. And what happens is you're going to measure the voltage from the voltmeter and the current from the ammeter over here. And then you're going to calculate the resistance by doing the voltage divided by the current. Obviously, and then you're going to put that value into your resistance here. Look at your table of results. You'll change the length, voltage, current, and then resistance over here. And then once you've done this, the resistance, don't forget, you can measure the length because it's stuck on the meter rule. And then the control variables is going to be the thickness of the wire. So you have to keep the thickness of the wire the same. You keep the surrounding temperature the same as well. The risk assessment, turn off the current in between the readings to stop the wire from heating up. So you turn off the current in between the readings to stop the wire from heating up. And finally, you plot the graph of resistance versus length. Hopefully you recognize that there's the length of the wire increases, the resistance of the wire will increase. Think about it like a road. The longer the length of the road, the more traffic there will be along the road. And resistance is the idea of traffic. Okay, so next thing. Thermistor then. What is a thermistor? A thermistor is simply a resistor which depends upon the temperature of its surroundings. Think of the word thermistor, so thermal resistor. And you get the following graph over here. You can see that as you increase the temperature, the resistance drops down. This is called a negative temperature coefficient thermistor. Why? Because it's going down. It's negative temperature coefficient. So as the temperature increases, the resistance decreases. So as the temperature increases, the resistance goes down. Now let's look at it in a circuit. So over here we've got a cell, I've got a bulb, and I've got the thermistor. So look, what happens if the temperature of the surrounding increases? If the temperature of the surrounding increases, the resistance of the circuit will drop down. If the resistance drops down, therefore the current will increase, and therefore the bulb will shine brighter. So make sure you can use a thermistor in a circuit, you know how it will influence the rest of the components. And by symmetry, if the temperature of the surroundings decreases, obviously we know that the resistance will increase, and therefore the current drops down, therefore the bulb will get dimmer. So make sure you can use this graph when you're tackling those questions over here. Next one, the LDR, the light dependent resistor. So light dependent resistor, very simply, it's going to be a resistor which depends upon the light upon it. So look over here, it's a rectangle with two lines going into it. This is a NTC LDR, negative temperature coefficient LDR. You can see as the light intensity increases, the resistance drops down. Yes, so as light intensity increases, the resistance drops down over here. And look at it in this circuit over here. So what happens as the light intensity of the surrounding increases? If I increase the light intensity, what happens is the resistance drops down, therefore there's more current, and therefore the motor will spin faster. Make sure you can see that, yeah? And obviously, as the light intensity decreases, yes, the resistance increases, the current decreases then, and therefore if this motor gets less current, it will spin slower. Direct current now. Direct current is simply current flowing in one direction only. This usually happens in batteries and cells over here. So look, the current will go in the same direction all the time. If I was to plot a graph of voltage against time, the line is a straight horizontal line because it's never changing direction. This is going to be direct current. Alternating current is simply going to be this. The current will go one way around the circuit and then it will reverse. And then it will reverse again. So it keeps swapping directions. So alternating current, the current changes direction. It goes one way and then it swaps around. So look at our graph of voltage against time right now. We can see the current goes one way, then reverses each time over here. So this is going to be the graph for the AC supply. For an AC supply, the voltage time graph looks like this. Alright, plugs right now. So we've got 3 wires right now. We've got live, earth and neutral. The live wire is brown and it brings the charge into the device and has a potential difference of 230 volts. The blue wire is the neutral wire and it's going to the left hand side over here and it carries the charge back down to the plug over here. It has a potential difference of 0 volts. The striped green and yellow wire, this one over here, is the earth wire, and this is a safety wire and it has also a potential of 0 volts. A nice way to memorize which way the wires are going is because if you take the second word of the color, look, second word of brown is R, sorry, second letter of brown is R, and T top, L left. You can see where this one goes to the right, this one goes to the top, this one goes to the left over here. The wires are made up of copper because they're a good conductors of electricity, and each of them are plastically insulated, obviously, so therefore they're not going to touch each other. The fuse is a very thin wire which melts if the current is too high, and therefore it breaks the circuit. There are different types of fuse ratings, guys, and look, it's found over here. Look, the fuse is over there. There's different types of fuse ratings: 3 amps, 5 amps, 9 amps, and 13 amps. The fuse rating tells you the current in which the fuse melts. So if you put 3 amps into a 3 amp fuse, it will melt it straight away. So a good idea is going to be the following. Let's say we had a kettle which uses 8 amps. Which fuse do I take? I choose the 9 amp fuse, yes? So you choose one just above it over here. For a kettle that takes 12 amps, I would take a 13 amp fuse. If the kettle had 5 amps, obviously I can't put the 5 amp fuse in because obviously it just blows straight away. So I must choose the 9 amp fuse for a 5 amp kettle. How does the earth wire work? Right, so how does the earth wire work? So over here, look, this is a toaster over here. And what happens is we've got a live wire going in, and this is the heating element of the toaster. And then you've got the neutral wire going back out again. Right, so this is the toaster working fine. So let's say for by accident the live wire becomes loose and touches the metal case. What will then happen is obviously the charge will then build up upon the metal case because the case is made out of metal. So that's obviously going to be dangerous because if you touch it, you're going to get a shock because it has a high potential difference and you will have a low one, it will jump onto you. So the following is helpful. They attach an earth wire to the metal case. The reason why is because now the charge can flow. All those electrons can now flow through the earth wire, down it, back to the plug over here. So that's the function of the earth wire. In case the metal case becomes charged, it now has an alternative route to flow through it back to the plug, keeping you safe. Oscilloscope traces. So over here, this is the best way to visualize signals. So basically it's like a piece of graph paper, but they haven't told you that the vertical plane is going to be the voltage, the horizontal one is going to be the time over here. Each square, it will have its value, so you can change the value of each square in terms of the voltage. So it will be either volts per division going vertically or time per division going horizontally over here. Right, so here's a good example of actually using the oscilloscope trace. Let's say we have an AC supply over here, and look, it's set to 2 volts per division. That's why every square is worth 2, and each horizontal one is 5 milliseconds. So the time one is 5 milliseconds. So if you want to work out the frequency, it's 1 over the time period. The time period is obviously going to be the time taken for it to go up and down here. So obviously 5, 10, 15, 20 milliseconds is the time period. That's why I put it over there. That's why 20 milliseconds convert to seconds. 20 times by 10 to minus 3. So I do 1 divided by that, it will be 50 hertz. So yes, 50 hertz will be the AC supply frequency. Okay, and the UK main supply is going to be 50 hertz and the voltage is 230 volts, everyone. So make sure you put this into your mind as well. So every single UK main supply is oscillating at 50 hertz, obviously AC, and the voltage is 230 volts. Right, electrical power now. So if you want to work out the electrical power of a component, it's simply going to be the current times by the voltage. So power is equal to current times by voltage over here. P is equal to I times by V, where power is measured in watts, current is measured in amps, voltage is measured in volts over here. And look, we can see that also, if you know that Ohm's law, V is equal to IR, I can replace the V with IR. It becomes P is equal to I squared R. Yes, because V is IR over there. Or if I rearrange this and say I is V over R, I can then replace the I over there. Power is also equal to V squared over R. So you've got 3 versions of this formula. Power is equal to I times by V, power is equal to I squared R, and power is equal to V squared over R. Voltmeters and ammeters. So a bit of basic stuff with regards to voltmeters and ammeters. The ammeter has minimal resistance to allow the maximum current to pass through it. over here, and the voltmeters over here have maximum resistance, so therefore it has to stop the current from going down this branch. It has to force the current to go through there. If this one had a low resistance, the current would simply bypass the component going round. Right, so now transformers. Why do we need transformers? So first of all, we know that electricity is made at power stations and it must be transported to our homes. If the current is too high, what happens is if you pass high current through a wire, the wire heats up. It's very inefficient because energy is lost as heat. So therefore you install transformers. You either put a step-up transformer and a step-down transformer in between the power station and the home. So look what the step-up transformer is going to do. It takes the high current and it makes it a low current. It does this by stepping up the voltage. So look, it takes the low voltage and makes it higher. It steps up the voltage to reduce the current. And the step-down transformer, it will reduce the voltage, there we go, to increase the current back up again, over here. So make sure you're happy with step-up and step-down transformers. And look at my summary statements over here. The step-up transformer increases the voltage to reduce the current. And look, if you look at the power formula, the voltage goes up, the current goes down for the power to remain the same. And the step-down transformer is going to decrease the voltage to increase the current back up again, over here, for the power to remain the same. The national grid is simply a system of pylons, cables and transformers used to help distribute electricity across the UK. It also responds to the changes in the supply and demand of electricity in the UK. So look, you've got power station, step-up transformer, a pylon, then look, then you obviously the wire, the cables going all the way from one pylon to the next, then a step-down transformer back to your home over here. So obviously the pylons are there to help hold the cables in place. And don't forget the function of the transformers is because you want it to be low current when it's being distributed, so therefore there's the least energy loss. Density. Density is equal to the mass of an object divided by the volume. Here is our formula. Rho is equal to m divided by v. The units for them, as you can see, are going to be green. If the mass is in kilograms and the volume is in meters cubed, therefore your density will be measured in kilogram per meter cubed. But sometimes you might find that you can use the mass in grams and the volume in centimeter cubed, and therefore the density will be in grams per centimeter cubed. So you can use kilogram over meter cubed or gram per centimeter cubed, depending upon the quantities that you've got. Required practical, the density of a regular object and the density of an irregular object and the density of a liquid. Right, so in order to work out the density of a regular object, so let's say we gave you this object over here, all you've got to do is the following. So first of all, you know that the formula is going to be mass divided by volume. So to measure the mass, you place it on a scale, you record its value of the mass. To measure the volume, you do the length times by the base times by the height, measured with a ruler. And then you simply chuck it into the equation. Density is equal to mass divided by the volume, and therefore you've worked out the density of a regular object. Control variables, you keep the block the same throughout the experiment. Density of an irregular object. So let's say you have an object over here and the shape is not uniform, it's all over the place, let's say like a set of keys. In order to work out the density of this, you can use a displacement can method. So here's my displacement can. It's basically a can which has a little spout right at the edge, right at the brim over here. Right, so what you're going to do is you're going to take the irregular object, you're going to drop it into the displacement can. So you fill it with water, drop the object into the displacement can, and what will happen is water will come out. Yes, so look, when you drop the object in, the water will come out of the spout over here, and you can collect the water over here. The volume of the fluid displaced, so whatever volume of the water that you have here, that is the same as the volume of the actual object. Okay, so now you've got the volume of it. In order to work out the mass, you just simply place it on a set of scales. So therefore you've got the mass, yes, by placing on a set of scales. You've now got the volume, simply measure this volume over here. Therefore you then use the formula density is mass over volume, and then you've got your density of an irregular object. Density of a liquid, right, so density of a liquid. So you need a measuring cylinder first of all, and you simply place it on a scale and you measure its mass, okay. Then you fill it up with a liquid, okay, then you place that on a scale and you measure its mass now. So you've got the mass of it empty, you've got the mass of it containing the water or the liquid, whatever liquid it is. In order to work out the mass of the liquid itself, you simply subtract them. So this, the mass of this, subtract the mass of this, will tell you the mass of the liquid itself. There we go. In order to work out the volume, simply read it off because it's a measuring cylinder, and then you've got the volume, and then finally from there you simply use the formula density is equal to mass divided by the volume to work out the density of the liquid. States of matter. So there are 3 states of matter: solid, liquid and gas. First of all, look, we've drawn them out over here. This may be a question, make sure you can draw them out. First of all, in a solid, the particles vibrate in fixed positions. They're in a regular arrangement, fixed pattern. There are strong forces of attraction between the particles. It's incompressible and it's a fixed volume. Liquid, the particles can slip past each other. There's irregular arrangement, yeah, so it's not in a pattern itself. There's moderate forces of attraction between the particles. It's incompressible, you can't squash the liquid down, and it takes the volume of the container. So let's say you put water into a teapot, it becomes the shape of the teapot. Gas, particles are free to move. The particles have high kinetic energy. There are minimal forces of attraction between the particles, and they take the volume of the container. So if I spray a gas in here, obviously it fills up the entire room. It takes the volume of the container over here. Then from here, we're going to talk about changes of state. So over here, we've got this diagram. We can see that we've got solid, liquid, and gas, right? And to go from solid to liquid, that process is called melting. Liquid to gas, obviously we're heating up even more. So the red lines indicate heat. It's going to be evaporating. And then blue lines mean you're going to be cooling it down. So gas to liquid is called condensing. Liquid to solid is going to be freezing over here. Then there's a direct route from solid to gas. Sometimes you can skip out the liquid phase. It's called the sublimation. And going from gas to solid, it's called deposition. When you're changing state, guys, the mass is conserved. So if I gave you 100 grams of ice, that would obviously end up being 100 grams of water, yes? Which would then be 100 grams of steam. The mass is conserved each time. Okay, now from here, we're going to plot a graph of temperature versus time. Let's say I gave you a piece of ice over here and we started to heat it up. We will notice that the temperature increases at the start, then it's going to go straight, then it increases again, then it goes straight, then it goes up one more time. Right, so first of all, the diagonal bits are going to be when it's in a solid, then the next state will be liquid, and the gas one over here. It goes, right now, you can see there's a horizontal line over here, and there's a horizontal line over here. The reason why is because there is no change in temperature at this point here. There is no change in temperature over here. The reason why is because the energy you are supplying, yes, to the solid, is being used to break the bonds. So we're going to break the bonds here, I'm going to break the bonds here. There we go. So there we go, horizontal lines, changing state, there's no heating. Diagonal line, the object is heating up, but there's no change in state. Okay, so you're changing states on the horizontal bits. Internal energy. The internal energy of a system is the sum of the potential and kinetic energy of the particles. The internal energy is equal to the sum of the kinetic energy of all the particles inside, plus the sum of the potential energy as well. Increasing the temperature of a system increases the kinetic energy of the system. Therefore, the internal energy of the system increases. That simply means if you heat up, let's say like a cup of water, the particles gain kinetic energy, and therefore the internal energy has been increased. And then from here, guys, at the bottom, we've got solid, liquid, and gas. If you were to go from solid to liquid, the potential energy increases. From liquid to gas, the potential energy increases again. From gas to liquid, the potential energy decreases. And from liquid to solid, the potential energy decreases. So make sure you're happy with how the potential energy varies as well. The specific heat capacity, right, specific heat capacity is going to be the energy required to change the temperature of 1 kilogram of a substance by 1 degree Celsius. The greater the specific heat capacity of a material, the more energy is required to change its temperature. And look, energy is equal to mass times by the specific heat capacity times by the temperature change. E is equal to mc delta theta, where energy is measured in joules, mass in kilograms. The specific heat capacity is joules per kilogram degrees Celsius. The temperature change delta theta will be in degrees Celsius. And look, here's an example over here. We can see that water has a specific heat capacity of 4,200 joules per kilogram degrees Celsius. And the specific heat capacity of oil is 2,000 joules per kilogram degrees Celsius. So we can clearly see that it would take you more energy to heat up the water than the oil. Yes, hopefully you should be aware of that with regards to cooking. Yes, it will take you more energy to heat up a pan of water compared to a pan of oil. And look, on this side over here, we've got a question in which we can use our formula. E is equal to mc delta theta. A bowl of mass of 100 grams is heated from 5 degrees Celsius to 45 degrees Celsius. Given that specific heat capacity of the water is 4,200 joules per kilogram degrees Celsius, calculate the energy. E is equal to mc delta theta. The energy, we're going to calculate that. The mass, 100 grams, convert to kilograms because our form is in kilograms. 0.1, 4,200 is going to be our specific heat capacity. The temperature change is 45 minus 5. And therefore, plugging it all in, you get the value of the energy is equal to 16800 joules. Specific latent heat now. So the specific latent heat is, first of all, it's different to the specific heat capacity. Specific latent heat of a substance is the energy required to change the state of 1 kilogram of substance with no increase in temperature. So this is what you're going to use when you're talking about it changing state. You're not heating it up anymore, you're just changing its state. There's a formula, it's going to be the energy is equal to the mass times by the specific latent heat. E is equal to ml. Energy is measured in joules, the mass is in kilograms, the specific latent heat of the material is joules per kilogram. And look over here, there are now two types. So obviously, whenever you're doing these calculations, recognize that one is the specific latent heat of fusion and one is the specific latent heat of vaporization. So this is the same formula, we've got just slightly different. I'll put a subscript over here. So E is equal to ml fusion, and this one E is equal to ml vaporization. Fusion, whenever I use that, I've got to be talking about solid to liquid or liquid to solid. So for any process going from solid to liquid or liquid to solid, I'm going to use a specific latent heat of fusion. For vaporization, it's the change of state from liquid to gas or gas to liquid. I've got to use this formula now. And then the formula definitions at the bottom for them separately. The specific latent heat of fusion is the energy required to change the state of 1 kilogram of a substance from solid to liquid with no increase in temperature. And the specific latent heat of vaporization is the energy required to change the state of 1 kilogram of substance from liquid to gas with no increase in temperature. Then from here, guys, we're moving on to this. So here's a couple of examples of it. So look, we can see that water has a specific latent heat of fusion of 334,000 joules per kilogram, and its latent heat of vaporization is 2,260,000 over here. Yes, so clearly we can see that the latent heat of fusion is not the same as the latent heat of vaporization. So on my graph, we can see that this bit over here, this horizontal bit over here, corresponds to the specific latent heat of fusion. So that's why the line is like this. The line is longer for this one over here. Why? Because it's vaporization and you require more energy. So look, for the water one, that's why it's 334,000 joules over here. And look, this requires more energy, hence why the horizontal line is longer. Make sure that you can actually identify them on your temperature and time graph. Multiple thermal changes. So this one was quite tricky, guys. So this is probably the top end of the course. This is, let's say we have this, we know that it goes from solid, then change state, then liquid, then change state, then to gas. They might ask you a tricky question in which you're trying to work out the total energy for this whole process. Well, recognize you need some energy for this bit, some energy for this, some energy for this, some energy for this, and some energy for this over here. The total energy to go from ice, let's just say we had ice, we're going to go to steam. You need to add all the energies together. So you need some energy there, 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 and there. So this bit will be the specific heat capacity of the ice, because you're heating it up. And then this bit will be the specific latent heat of the fusion of water. Then this will be the specific heat capacity of the water, yes, because you're heating it up. Then again, then this one will be the specific latent heat of vaporization of water, yes, over here. And last of all, the specific heat capacity of the steam, this bit over here. So therefore, 1, 2, 3, 4, 5 processes over here. And that's why I look at my formula, that's coming from there. And there's the second one there, MC delta theta there, ML vaporization over there, MC delta theta for the last one over here. So this is when you have to add all the energies up for the entire process, going from all the way over here to all the way over there. This is a tricky topic, so if you're still struggling, look at my playlist down below. I've got a whole exam walkthrough just on these questions here. Brownian motion now. So over here we have the following. We have, let's say, a petri dish full of water. I've got some pollen grains in there. So when you look at them under a microscope, the pollen grains are seen to be moving around. Yes? Okay, jiggling about. The reason why is because the pollen grains are being hit by the water particles from all directions, yes, at different speeds and random motion, yes? So in different speeds and random directions, that's how the water particles are moving. And that is known as Brownian motion. It tells us that the particles are moving in a random motion and at various speeds. And that's how gases behave. Gas pressure. So first of all, gases actually have pressure. If you've forgotten, pressure is equal to force divided by area. So particles, let's say we have a box over here, the particles are moving around. Every time they collide with the wall of the container, they exert a force. Yes, every time they collide. So now we've got collisions, force acting over a unit area, hence why there's a pressure. So gases have a pressure due to this reason. It's because of the collisions of the particles against the walls of the container. Gas pressure and temperature, right, so what happens if we were to increase the temperature of a gas? So let's say we have a gas over here and we are going to heat it up, right? We're going to heat up, hopefully we identify that the particles are going to gain kinetic energy and move faster. If they move faster, they travel faster across and they collide more often with the walls of the container. So when there are more collisions per second, obviously there's going to be more force acting per second as well. Therefore, we know the pressure will be higher. So as you increase the temperature of a gas, the pressure increases. Pressure in a fluid. Let's say you were asked to work at the pressure in a fluid. So let's say we have a swimming pool over here. We can see that the pressure inside the fluid can be calculated by the density of the fluid times by the gravitational field strength of the planet that you're on times by the height of the fluid, yeah, or height of the column, yeah, how far from the surface that you are. P with the pressure is equal to rho GH. P is pressure measured in Pascal, PA. The density is going to be kilogram per meter cubed. Gravitational field strength is newtons per kilogram, and the height will be meters over there. There we go. And look, on the right hand side I've got another example of this. You can pause the video to look at that. Just a simple question practicing the use of that equation. Gas pressure and volume now. So gas pressure and volume. So over here we've got the following. We've got a gas in a container, and let's say we were to right now we were to squash it down. What would happen to the pressure? Well, if you reduce the volume, what happens is obviously we reduce the volume, there's less space for the particles to travel. So therefore there are more collisions per second, and therefore the pressure will increase. So by reducing the volume, the pressure will increase over here. We end up with the following relationship. If you plot the graph of pressure versus volume, it's going down, inversely proportional. Pressure is proportional to 1 over the volume. P is proportional to 1 over V, and therefore the pressure will be equal to, moving from here to there, you just put a constant mathematically, a constant divided by V. Therefore, moving this up, pressure times by the volume will be equal to a constant. Okay, so along that line, the constant remains the same. If you take any value of the pressure and the volume along this line over here, they will have the same constant. Then this leads us to the following. So let's look at the following graph. We've got pressure versus volume. I've got a volume V1 over here, the volume here, V1 and P1. And over here, I've got the final volume V2 and the pressure P2. We know that P1 times by V1 is a constant, yes, for these two. But we also know that P2 times by V2 will also be a constant. Because the constant is the same for both of them, I can equate them both. So P1 times by V1 is equal to P2 times by V2, leading us to this expression over here. Then work done on a gas. Okay, let's say we have a container full of particles over here, and let's say that one of the walls of the container are compressed rapidly. So you rapidly squash it down over here. What's going to happen is as you move this wall closer very rapidly, the particles will hit the wall. And don't forget, if you move this and the particles are hitting the wall at the same time, they will gain kinetic energy. So therefore, the pressure will increase. There we go. So this is when work is done on a gas over here, because you've exerted a force on the particles as you've squashed down the wall over here. So the particles now gain kinetic energy because you've squashed it down, and therefore this increases the internal energy of the system. Work is being done on the gas because you are squashing it down. That's the reason why work is done on the gas, and work done is energy transferred via forces. Atmospheric pressure now. So let's say on the top left hand side, this is the Earth's surface. We can usually talk about the air being uniform, of a uniform density over here. But in reality, the Earth's surface is not like that. The Earth's surface is more like this. There's a greater density at the bottom and there's less at the top. Okay? Hopefully you know the reason why. It's because gravity is acting and it drags all the particles down over here. Plotting the graph of pressure versus altitude, we can see the following, that as you get further and further away from the Earth's surface, the pressure will decrease. And once again, we can use our formula for pressure for the fluid. Don't forget, this is a fluid, so we can use pressure is equal to the density of the fluid times by gravity times by the height, the same formula we looked at earlier on. Right, atomic structure. So over here we have an atom. We can see we've got protons and neutrons inside the nucleus over here. Electrons are orbiting over here. Here are my symbols. So proton, there we go, is a charge of +1. Think of P for proton, meaning positive, the relative mass of 1 as well. Neutron has a charge of 0, it's neutrally charged. Think of neutral over here. relative mass of 1. The electron over here, it's orbiting the nucleus. It has a charge of -1 over here. Its relative mass compared to the other ones is going to be 1 over 2000 for this one over here. Right, now, nuclear notation. So sometimes you'll see chemical elements over here, and they're represented in this fashion over here. There's a number at the top, a number at the bottom. The top number corresponds to the number of protons and neutrons. The bottom number corresponds to the number of protons. Yes, this was going to be the atomic number at the bottom and the mass number at the top. And the chemical symbol goes over here where the X is. So look, this is helium 4-2He. The reason why it's 4 is because there's 2 protons and 2 neutrons. In total, there's 4. But there are 2 protons. That's the reason why the bottom number is 2 over there. And yes, the proton number is usually the number of electrons as well. So there we go. So 2 protons, and therefore there are 2 electrons as well. The radius of an atom is going to be 1 times by 10 to the minus 10. And the radius of a nucleus is roughly 1 over 10,000 of the radius of this atom over here. So just make sure you recognize that the nucleus is tiny compared to the actual radius of the entire atom itself. Isotopes. Isotopes are atoms with the same number of protons but a different number of neutrons. So over here we've got 1, 2, 3 different isotopes of helium. This one is helium 4-2, this one is 5-2, this one is 6-2. As you can see that they have the same number of protons. Red is protons, yes, so 2 protons, 2 protons, 2 protons, but the number of neutrons are changing. Hence why it's going to go from 4 to 5 to 6, because this one, there are 2 neutrons here, so therefore there's 4 nucleons in total. This one is 5 in total in the nucleus. This one is 6 in nucleus, hence why it's over here. So isotopes have the same number of protons but a different number of neutrons. History of the atom. You've got to be aware of how the model of the atom has changed as time has gone on and how we've discovered new things about the atom. So first of all, there was a model that basically atoms were tiny, spherical, indivisible, over here, and then we moved on to the plum pudding model. It was just going to be a giant positive charge, a solid block, and negatively charged electrons embedded around it. Very similar to a pudding. Yes, that's the whole point. It's a plum pudding model. Some kids don't like that. You can think about it as a chocolate chip cookie, and the electrons are like the chips which are embedded within the cookie. It's the same idea, but it's a giant positive charge and there are negatively charged electrons embedded. There is no free space in this, and the electrons are not free to move. And then from here we move on to the Rutherford's model over here, which is the nuclear model. He found out that in the center there's a positive charge over here in the nucleus. This is called the nucleus, and it's positively charged, and electrons are orbiting it over here. Electrons are orbiting it over here. Make sure you can identify that there are no neutrons right now. The reason why, they haven't been discovered yet. But there's a big flaw in this. So obviously if this is positive, this is negative. Hopefully that you can see that they would collapse because they would be attracted towards each other. So that led us to the Bohr's model of the atom, in which he stated that there were protons and neutrons inside the nucleus. The neutrons were discovered by James Chadwick, and the electrons are orbiting in fixed shells. So now they are electrons in fixed shells, not just whizzing around it in an orbit over here. And the electrons, because they are in fixed shells, they cannot drop down. Right, how on earth did we get to Rutherford's model? It's going to be via the Rutherford alpha scattering experiment. So what he did was this. He took a radioactive source which was going to emit alpha particles. For now, just accept that these are some radioactive particles which are positively charged. So positively charged particles are coming out of this source over here. There's a lead-lined container around it to just block off any alpha particles which might go back. And then the alpha particles are going to travel across. He fired them at a thin layer of gold foil over here, and he put a Geiger counter on the opposite side over here. The Geiger counter detects the alpha particles. Every click the Geiger counter receives tells you that an alpha particle has been detected. And look, I've got a counter over there. So obviously if loads of them can pass through, this number goes up. Here are his results, guys. So look, you can see that most of the alpha particles pass straight through. Some of them were deflected, okay? And then very few of them were deflected at extreme angles. Very, very few of them are deflected at extreme angles. What did that mean? Right, so look, this diagram is what I usually use to explain it. So look, I've got the alpha particles going over here, and look, they're all going across. And this is the atom, the atom that obviously he was proposing. This kind of makes sense now, because you know that most of the atom is empty space, hence why most of the alpha particles can pass straight through. So look, this one passes through, this one passes through, this one passes through, and these ones at the bottom over here. Then, as some of the alpha particles get closer to the nucleus, hopefully you recognize that the alpha particle is positively charged, the nucleus must be positively charged because it's going to deflect them away, because like charges repel, and that's the reason why it deflected away over here. And then some of them were deflected by extreme angles over here. So what does that mean? That means that it's The nucleus is a tiny concentrated mass within the atom itself. That's why it's very hard to fire at it directly and hit it head on. So look over here, we've got the following observations. Most of the alpha particle passes straight through because most of the atom is empty space. Some of the positively charged alpha particles were deflected. The reason why is because they are repelled away from the positively charged nucleus. And last of all, very few alpha particles were deflected by extreme angles, almost 180 degrees. The reason why is because the positively charged nucleus is a concentrated mass over here. Make sure you know the difference between these two, the last two. As most kids get them confused, make sure you know the difference. Electron transitions and radiation. So let's say we have the atom over here. First of all, an electron can move to a higher energy level, so it can go from this one over here to upwards over there if it absorbs an electromagnetic wave. So look, I've drawn it over here. So look, we have this one over here, we have this electron over here. So look, an electromagnetic wave can come in. This electron can absorb this energy of this electromagnetic wave and move upwards to a higher energy level. So there we go, the electron is promoted to a higher energy level. And by reverse, let's say you had an electron at the top right now, but it wants to go back down. Obviously, it drops back down to this lower energy level, releasing a corresponding electromagnetic wave. Radioactivity, right, so first of all, let's say we have a nucleus of an atom over here. First of all, the nucleus is stable, nothing will happen. Yeah, nothing will happen here, it's just stable. Yes, like most of the stuff around us. But if the nucleus becomes unstable, usually when it's too heavy, what happens, it will break down. Yes, and this is known as radioactive decay. So when the nucleus breaks down, this is known as radioactive decay. In a decay process, what can happen is the large unstable nucleus can break down and it can become into two smaller pieces, and sometimes you might get alpha radiation coming out, beta radiation coming out, gamma radiation coming out, or neutrons. Sometimes only one of them, but I've drawn all of them over here. And energy is released in this whole process. So when a decay process happens, we get all of these things possibly coming out. Right, so how would you detect alpha, beta, and gamma? So let's say obviously the decay process occurred. How would you detect alpha, beta, and gamma? First of all, you can use the Geiger counter. So look, you can put your radioactive source over here in a lead-lined container. Yes, the reason why we'll come across that in a minute. And what happens is the alpha particles travel outwards and the Geiger counter will click every time an alpha source is detected. Yes, or beta source or gamma source over here. The activity is basically the amount of radioactive particles detected per second. There we go, the amount of ionizing radiation detected per second. The units of activity are called the becquerel, capital B, lowercase q, the becquerel over there, or counts per second or counts per minute. Right, background radiation. Background radiation is the radiation that naturally surrounds us from our environment. It is dependent upon many factors including jobs and location. These are the naturally sourced ones over here. Radon gas from rocks and buildings, cosmic rays from space, radioactive material in food and drink. Man-made ones, so obviously if you do these jobs or you're around these areas, you will get exposed to more radiation. X-ray equipment, imaging, nuclear fallout from nuclear weapons, so if there's a nuclear disaster in the area, nuclear accidents such as Chernobyl or Fukushima. Obviously if you live near a nuclear power plant which obviously collapsed, you'd have more radiation. The radiation dose is measured in sieverts, capital S, lowercase v. Investigating radioactive sources. So let's say you were asked to actually measure the radioactivity of a source. First of all, you should measure the background radiation in the room. So you have the Geiger counter, you measure the background radiation in the room, which is going to be my green arrow. Okay, so let's say right now I measured it for 1 minute, I've got 10. Yes, 10 clicks in 1 minute. Then if I was to put a source in front of me, I would measure the count rate again. So let's say it's 180 over there. So obviously, the reason why it's higher is because now you have the source plus the background radiation. Therefore, to work out the activity of the source itself, you simply take this value and subtract the initial value over here. So the count rate of the source is equal to the count rate of the source plus the background radiation, which is this one, subtracting the count rate of the background radiation over here, subtracting this one over here. So it's going to be 170 is actually coming from the source because you've excluded the radiation from the background radiation. Properties of alpha, beta, and gamma. So this table you should hopefully memorize that we've got alpha, beta, and gamma over here, and I've got the symbols of them. Alpha 4,2, description of alpha particles, 2 protons and 2 neutrons, like a helium nucleus. The charge is +2, why? It has 2 protons. Relative mass is 4 because there are 2 protons and 2 neutrons. Each one of them is worth 1. It is stopped by 10 centimeters of air. Okay, and it's the least penetrative, but it is the most ionizing. I'm going to come across these two bits later on, so don't worry. Beta, symbol of 0, -1, beta over here. It's a fast-moving single electron. The charge is -1. The relative mass is 1 over 2,000 because it's just an electron over here. it is stopped by thin metal sheets. Yes, it can pass through paper, but it is stopped by thin metal sheets. The penetrative ability is moderate, ionization ability is moderate as well. Then gamma over here, 0, 0, yes, because it's a wave, it's an electromagnetic wave, there we go. The charge is 0, the mass 0 as it's a wave, stopped by thick lead or concrete. Penetrative ability is the most, it can pass through the most. Ionization ability, it is the least. And here's a nice visualization of the penetrative ability. So look, alpha, stopped by paper, beta, pass through the paper, stopped by thin metal sheets, gamma, pass through the paper, pass through the thin metal sheets, but stopped by the thick lead or concrete. So as you go down the group, the penetrative ability is increasing. Nuclear decay equations, right, so when a nucleus undergoes a decay, alpha, beta or gamma, the nucleus will change itself. So we can look at how the atomic mass and the atomic number changes. So over here, look, we've got 235, uranium 92. So first of all, if it undergoes alpha decay, the alpha decay leaves, taking a 4, 2 away with it. What happens to the nucleus that's left over? Obviously, I must subtract 4 from the top number and 2 from the bottom one. But look, they balance out. 235 uranium goes to make 231 thorium, plus the 4 over here. So these two numbers add together to make this number over here. 92, obviously, it becomes 90 because the 2 is taken over there. For beta minus decay, look carefully, the beta is 0 minus 1. So look, the mass number remains the same. 235 goes to 235 because 0 is over here. These two add up to 235. But careful with this one, we notice that it is 93 because it must be 93 minus the 1 makes me 92 over here. So in beta decay, one of the neutrons inside the nucleus is converted into a proton, hence why the proton number goes up over here and the beta particle is emitted. There we go. Right, now gamma decay. As you can see, gamma 0, 0, therefore the mass number remains the same and the atomic number remains the same as well because it makes no change over there. So 235 goes to 235 plus 0, 92 goes to make 92 plus the 0 over here. This bit's a bit extra, but beta positive decay. So yes, beta particles can be a positive version of it. As you can see, in beta positive decay, one proton in the nucleus is converted into a neutron. So we're going from one proton in the nucleus is being lost and being converted into a neutron. That's why, look, 92 goes to 91 because we've lost a proton, but the mass number remains the same. And the beta positive particle takes away with it the 0 and 1 over here. Ionization ability, right, so I usually use this to explain ionization ability. We can see that we've got alpha, beta and gamma, and let's say we fire them through a group of atoms over here. First of all, to ionize something is to rip off an electron from an atom. So we can see that as the alpha particle moves through it, because it has a charge of +2, it can knock out the most electrons. So that's why it's highly ionizing, but it travels the least distance. Beta particle, it's only a charge of -1, so it can knock out a bit more than the alpha. And gamma is the least ionizing, so therefore it interacts with the least amount of electrons over here. So we hopefully can identify that alpha, beta and gamma as you go up. So alpha is the most ionizing, beta is the moderate one, and gamma is the least ionizing. Half-life. The half-life of a radioactive sample is simply the time taken for the number of nuclei within a radioactive sample to decrease to half of its initial amount. Right, so let's say we gave you all these nuclei over here, red, they're undecayed, but as time goes on, they're going to decay. So look, they all turn blue over here. So obviously as time goes on, they all decay. If I was to plot the graph of number of undecayed nuclei, so look, we've got loads at the start, okay, and as time goes on, they will decay. So as you can see, guys, as time goes on, the number of nuclei decreases. Over here, it's an exponential curve downwards. Right, so now from here we can actually look at the half-life on this graph. So look, the half-life to work it out. So first of all, the initial amount is 1,000. You simply look at where 500 is and read off the graph over here. So the time taken for the nuclei to drop down to half of its initial amount is obviously from 1,000 to 500. It's only going to be 10 seconds for this radioactive sample over here. Make sure you draw that on the graph over there. Right, so now from here we're going to look at the uses of nuclear radiation. So over here, this is the physics behind a smoke alarm, and it actually uses nuclear radiation. So here we've got a cell, and we've got a terminal over here, and they place an alpha source on one side. Right, so the alpha source over here, what's going to happen is obviously it will emit alpha particles, they will travel across the gap over here. So now look, you've got a flow of charge, because the alpha particles are charged, they can cross the gap, there will therefore be a current as it goes around the circuit. But then when there's a fire, what happens is obviously smoke particles enter the chamber, right? So now look, the alpha particles are blocked from going across, and therefore the circuit identifies that there's a drop in the current, and hence the alarm sounds. And this is the reason why we actually use alpha radiation inside a smoke alarm. Right, using beta decay to measure the thickness of foil. So how they actually keep the foil that's in your kitchen like that thin is going to be via this method. Right, so over here you've got some giant bit of metal coming in, all right, now so a slodge, and what happens is there's two rollers here. The rollers are designed to squash all that metal into a nice thin strip over here. So there we go, it enters on one side and it uses the rollers to squash them over here. So what they do is they put a beta source on one side of what's coming out. So this is the very thin strip coming out, and a Geiger counter underneath it on the opposite side over here. So the beta source is going to emit the radiation, it's going to travel down and through it, and we will get the Geiger counter getting a reading because some of it can pass through. Right, so simply by looking at the Geiger counter you can determine the thickness of the foil. So over here we can see that the thickness of the foil has gone up from 100 to 200 over here. So what does that tell you? So obviously that means that if there's loads more radiation being detected, that tells you that the foil is too thin, okay? And therefore you can separate the rollers to increase the thickness of the foil. And what about this one over here? Let's say that the count rate drops down too much. Obviously, if the count rate drops down too much, that means it must be too thick in the middle. That's why less beta particles can pass through. And therefore, if it's too thick, you can move the rollers closer together to squash it to make it thinner. Medical traces. So let's say, unfortunately, someone has a tumour over here in an unknown location within the body. So first of all, we can use a radioisotope medical tracer to pinpoint its location. So the person ingests a radioisotope, it goes inside the body. The radioisotope then is expelled, it's going to travel out of the body over here, there we go. But because you have a tumour, the tumour will absorb an excessive amount of the radiation. Okay, so the tumour absorbs a large amount. So let's say then after a period of time you were to come back to the patient and you look at the radiation that it should be given off, you would find that most of the radiation would have disappeared, but because the person has a tumour which absorbed a large amount, it would still be given off the radiation. And hence that's how you can find out the location of a tumour using a medical tracer. Right, so now from here, when choosing a radioactive isotope tracer, you obviously must look at the dangers and the half-life of the sample. First of all, the reason why gamma is chosen because you know it can pass through the skin and it can pass outside of the body. Yes, it can pass outside of the body over there. It is also the least ionizing, so you don't want to put alpha inside the body. And then, first of all, the half-life. You do not want it to have a very long half-life because the person will be exposed to a large amount of radiation. Nor do you want the half-life to be too short that you can't actually carry out the experiment. You don't want it to put it in the body and therefore it quickly leaves it over here. So you don't want a too long half-life, not a too short half-life over here. So make sure you are aware of that when choosing the radioactive medical tracer. Next one, the gamma knife. So the gamma knife is this, let's say you have a tumour, let's say in a location in your head. First of all, you just put radioactive cobalt sources at different angles over there around you, and obviously they fire out the radiation, and hopefully where all the beams cross over here, it targets the target area and destroys the cells over there. So yes, alpha, beta and gamma are all ionizing, and yes, they can lead to changes in your DNA and therefore mutations and lead to cancer, but it is, as you can see, it can be used to treat cancer as well. Right, so the half-life and half-life calculations. Right, so first of all, radioactive dating. So this is how we actually work out how long something has been dead for. It's via the process of radioactive dating. This is a person over here, and first of all, every single person alive is constantly taking in carbon-14 from the food that you eat. Carbon-14 is a radioactive isotope, and it decays as time goes on. It has a half-life of 5,700 years. Okay, so it has a half-life of 5,700 years. Okay, so right now let's start with the following. Let's say we have 1,000 grams of carbon-14 taken into the body right now. Okay, let's say this person over here has 1,000 grams. But let's say if the person dies, what will actually happen is obviously you're not taking in any more carbon-14, it will decay. So the amount of carbon-14 inside your body will decay as time goes on. So as you can see, the amount of carbon-14 has decreased over here. And that process to go from 1,000 to 500 is one half-life, because that is the definition of the half-life. So that would take me 5,700 years. So here's a good example of radioactive dating. So look, a fit person should have 1,000 grams of carbon-14 inside them. A body is found with 125 grams of carbon-14. The half-life of carbon-14 is 5,700 years. For how long has the body been decomposing? The way you tackle this question is the following. So we've got 1,000 grams over here when you're alive, but the body that you found has only got 125. First of all, you know you should have 1,000, but you've got 125. Work out how many half-lives have passed. So look, it's going from first half-life, second half-life, third half-life over there. So 3 half-lives have passed to go from 1,000 to 125. And then from there, you know each half-life is worth 5,700 years. Therefore, it's just going to be 3 times that. There we go, so 17,100 years. If you're still struggling on this, I've got loads of videos on me going through difficult half-life questions in the description below. Right, now, nuclear fission. Nuclear fission is the process in which a large stable nucleus splits into small, lighter nuclei releasing energy. The energy comes from the mass difference between the initial nucleus and the products afterwards. So the mass of this nucleus is not equal to the mass of this one plus this one. Why? Some of the mass has been converted into energy. So induced nuclear fission. So this is what occurs inside a nuclear reactor. Basically, they have uranium, yes, which is stable, or yeah, over here. What they do is they fire a neutron into it, and then look, you know, the neutron goes in, it becomes unstable, and then it starts to split. There we go. It actually splits off into two daughter nuclei because they come from the parent. That's why it's called daughter nuclei, and 3 neutrons are released plus energy. Okay, and look over here, you can see that one neutron goes into uranium, it becomes uranium-236. Krypton barium are released, and 3 neutrons plus energy is released in this process. Right, so there's something interesting that happens to these 3 neutrons which are released. Those 3 neutrons released from the initial fission reaction. Yes, this is called induced fission because you are triggering it with the neutron. That's why it's called induced fission. The neutrons released will then hit other uranium nuclei and they will then split themselves. So from one initial neutron, we're getting this split, these splits, and these splits occurring over here. And therefore, each time this occurs, energy is released in the whole process. Right, so now, how would you control this? This can actually spiral out of control with too much energy being released in a short amount of time. So the simplest way is to absorb the excess neutrons. So you can actually put like blocks inside, you know, these are called control rods, and they are placed inside to absorb the excess neutrons. They are made out of boron. So the excess neutrons are absorbed by the boron here. Now let's look at all of this within a nuclear reactor. So hopefully you remember that a nuclear reactor core is going to produce energy in the form of heat. It then heats up the water, which turns into steam. The steam then goes through the turbines turn, which connects to the generator, which creates electricity. So what does a nuclear reactor core look like? It looks like this. There are things which are called fuel rods, which are separated. Yes, they're not touching each other, they're separated. In between each of these fuel rods, there is a control rod. Okay, the fuel rods contain the uranium or whatever fuel that you're using, could be plutonium over here, and the control rods are over here. The control rods can be raised or lowered. The whole thing is has been encased in concrete. Yes, the reason why it stops all the excess radiation being emitted to the surroundings over here. Right, and look, all of it's in water. Yes, and there's a heat exchanger over here. So looking over here, we can see that when a neutron is fired in, what happens is, yes, the uranium splits, releasing neutrons, and they can then travel into the other fuel rods, causing multiple fission reactions to occur. But let's say the reaction is happening too fast, you simply can insert the control rods down, and obviously they block off the neutrons and obviously slow down the rate of the nuclear reaction. So that's the use of the control rods. And over here I've got a table just summarizing it. Fuel rods contain the nuclear fuel which will undergo the fission. Control rods are raised and lowered to absorb the excess neutrons. There's also a moderator which slows down the speed of the neutrons so that they can be easily absorbed by other uranium nuclei. So that means that if, imagine the neutrons are traveling too fast, a uranium nucleus can't absorb it. It's like someone throwing a ball at you really fast, you can't catch it. The heat exchanger is used to remove heat from the whole system, so therefore it doesn't overheat. And then shielding is the concrete shielding on top, just to prevent the radiation from escaping. Nuclear fusion. Nuclear fusion is the other process. So rather than having nucleus splitting and releasing energy, you can take 2 lighter nuclei, combine them into one which is heavier, and that will release energy. It's almost like the reverse. So nuclear fusion is a process of when 2 lighter nuclei combine together to form a larger, heavier nucleus, releasing energy in the process. Okay, the energy comes from the mass difference again. So the mass of these two will not be equal to the mass of that because some of the mass has been converted into energy, which is going to be released over here. The reason why this is difficult is because, don't forget, both the nucleus are positively charged. Yes, there's loads of protons there, loads of protons there. Therefore, they will be repelled from one another. So therefore, you need high temperatures and high pressure for this to occur, which are really difficult to achieve on Earth. Nuclear fusion, though, can be found naturally within all the stars. So all the stars are powered by nuclear fusion. They are fusing hydrogen into helium. So they get hydrogen, it's fused into helium, and that's what produces the energy which we have on Earth over here. The differences between nuclear fission and nuclear fusion. Nuclear fission, large nucleus splits into 2, releasing energy in the process. The energy becomes from the mass difference. Nuclear fusion, smaller, lighter nuclei combine to make a larger nucleus, releasing energy in the process. Energy comes from the mass difference again. Nuclear fission, there's a finite amount of uranium and plutonium available. There's only a limited amount on Earth. But nuclear fusion, if we manage to solve this and actually get this working. There's an abundant fuel. Imagine if we can actually fuse water. Water can be theoretically used, could potentially solve the energy crisis. Per kilogram of fuel, fission releases less energy. Per kilogram of fuel, fusion releases more energy. Fusion reactors are easy to get started and the science behind them is well known. Fusion reactors are very difficult due to the high temperature and high pressure. And last of all, the difference between contamination and irradiation. Contamination is when a radioactive material actually physically gets transferred onto something. I always give the example of, imagine a fly, it touches something dirty and it lands on your food, it's contaminated it. It's actually transferred the physical matter onto something new. So if something radioactive has actually physically attached itself to you, you've been contaminated. Irradiation is different. It is simply being exposed to the radiation. So as you can see over here, the radioactive material hasn't touched the person, you're just being exposed to it. So there is a difference between contamination and irradiation. And that's it, everyone. That is everything you need to know for AQA Physics Paper 1. Yes, and that is everything that I have. I've tried to, just pour it all out on camera, and hopefully it helps as many kids as possible. I know it's a challenging subject. Yes, it's definitely not easy. There are definitely easier subjects in physics, but hopefully I've been able to break down some barriers for you and clarify some concepts that maybe you've been struggling with before. You should use this video for, let's say, revision before the actual exam, maybe the night before or a couple of weeks beforehand. And obviously, the more you view it, the better it will get in terms of your understanding. If you don't understand something, just comment below and I will do my best to answer all the queries. And obviously, we can learn from each other as well, because obviously it helps. Yes, I might be able to explain stuff a bit more clearly for you. Just drop me a line, I'll be able to help you here. On my website, there's going to be more resources coming out. And I'm going to be offering academic tuition as well, obviously in the preparation for the exam. Get in contact via my website if needed. Okay, everyone, ciao, ciao, and goodbye, and good luck in your exams.